Part 2. Power in multiple load systems. So, problems where multiple real and reactive loads connected to a single source can be solved by simply summing all the individual real reactive components together, as in this example. So we're going to look at an example now, and there's a way of drawing it that kind of simplifies all the power flows. So we got a 400 volt power service point here, and we got connected to it 1, 2 pure resistors, a motor, 2 inductors, and 2 capacitors, all connected to the same supply. Yeah. And what we're able to do is add up the Q contribution of each, add up the P contribution of each, add up the and then use that to get the overall P, the overall Q, and work out what the S is for the whole load. Okay. Now, what we do is redraw the system so it's got like the supply up here. That's our 400 volts. Okay, and then C1 is a capacitor. Capacitors give Q back to the supply. Yep. So the arrow's pointing in. Inductor takes reactive energy from the supply. So the arrow's pointing out. A resistor, that's going to be power. So these are going to be Qs. Inductors being positive Q. Capacitors being negative Q. Yeah. This is an inductor, so it's a Q. Resistor as a power. Capacitor as a negative Q. What's a motor? That's going to have both. It's going to have a power, but it's also going to have a Q in the inductive part too. Yeah. If you look for the specification of the motor, let's just go back to the bigger diagram. That's 13 kilowatts, 7 kVAR. Yeah, well, that might not be in that form. That might be in kilowatts and power factor, or cos theta. So I'll tell you what the power factor of the motor is. From that you can work out. You might be able to get it from the line current. Okay, but in this case I've put that that's 13 kilowatts and that's 7 kVARs. Alright, so system is redrawn as a system of single line power buses and arrows used to indicate power flows. Remember, inductors are said to draw reactive power from the system, positive kVAR. Capacitors give it back, negative kVAR. Motors draw both real power kilowatts and reactive power kVAR. Yep. So, what we're going to do here then is calculate the total reactive power drawn from the supply, the total real power drawn from the supply, the apparent power drawn from the supply, find the line current, and find the power factor of the complete system. Yep. So we'll go through this one together. What we can do is say QT is equal to, and then we've got all the positive ones, so that's going to be L1, QL1, 3.5. They're all in kilo, these quantities, so we can just add all the numbers up and the answer will be in kVAR. we've got L2 3.2 and we got M1, which is 7 kVAR, and then we got C1, which is minus 9 kVAR, and C2 minus 12 kVAR. The total of all that is minus 7.3 kVAR. So we just add them all up, we got the total Q. So that's 1. 2. Total power. We just take all the individual powers. So that's 6 kilowatts for R2 plus 2.5 kilowatts for R1 plus 13 kilowatts for the motor. That's 1921.5 kilowatts. Now, how do we find the apparent power drawn from the supply? Yep, we've got two sides of our power triangle now, haven't we? Alright, this is 21.5. This is minus 7.3 kVAR. We haven't got an angle in there yet. And S T is on that side. So we can find that by Pythagoras. It's equal to PT squared plus QT squared, all square rooted. It's root of 21.5 squared plus 7.3 squared. Doesn't matter about the negative sign because squaring that's going to cancel that anyway. Equals units, James? It's kVA in this case, because all the values we've used are multiplied by 1,000, aren't they? Are all K's. Alright? 4 IL, the line current. What's another formula for S? Well, E times I, the line current, IL. Yeah, so we can rearrange that, can't we? So it's S over E. $22,700 here, because our volts are in volts and not kilovolts. We need to go to 22,700 over 400 equals. We'll take 56.8 then, young friends. Okay. power factor. 5 power factor is equal to what? How do we express that power factor? Yes, it's cos theta, which is equal to, in terms of this triangle that we've got, it's going to be no, we want S, don't we? So we've got to use, this is the angle we want. There's got to be Q ST, hasn't it? No, hang on, P, patient side, cosine, isn't it? P over ST. So that's 21.5 over 22.7. Jolly good power factor, I'd say. 0.947. Yeah. Okay. So that'd be a reasonable exam question, but what I might do in an exam question in terms of that is probably devise one that had a worse power factor for that, and then maybe add to that, improving that power factor with an extra capacitor or something like that to improve the power factor from 0.7 to 0.8. Yeah, we had a little bit of go at doing that last week anyway, so that might be incorporated into a load center question like that. All right. In the tutorial questions this week, there's probably at least one question around that type of thing as well. Anyway, all right. That was an extra page to allow a bit more room if I needed it. Right. Solving AC circuits using the power triangle method. So, looking at that circuit there, we've got a voltage arrow here, and we call this question was taken out of a book. So that's V12, the voltage between the terminals 1 and 2. No value given. We've got the fact that we've got a line current flowing in the direction shown by the arrow. We've got an 8 ohm inductor in series with the line. After that inductor, we've got terminals 3 and 4, and I said 1. Between 1 and 3, 60 volts. And that's connected to a 5 ohm capacitor and a 12 ohm resistor in parallel. And the question is asking, calculate the current in each circuit element, the voltages between terminals 1 and 2, and the impedance between terminals 1 and 2. Okay, so we're going to go through how we can solve that problem together now. Alright? Yeah? So I'm going to go on to the next page because I've got the circuit on the next page a little bit smaller, I thought. Maybe they have anyway. No, older. I know what I must have done. I must have done this, I reckon. Let's just pause that for a what we got. What don't make sense about it? Rectangular. Have you? No. Are you in Are you in degrees for a start? Yeah. So here's 0. Yeah. And we're going more than 90 degrees, but we're not going 180. So we're in that quadrant. So is it a negative real part? Yeah, no, but you'd expect a negative real part because it's left to right on there. Yeah. So knowledge of quadrants is handy there. That's a little check. Does it work with quadrant 2? Quadrant 2 is negative real part, positive j part. Quadrant 3 is negative both. And then quadrant 4 is negative j, positive real. And in this one, they're both positive. Alright? So, yes, the negative result is correct, and it is. Plus 39. So that's 40j really then, isn't it? Yep. So minus 96.01 plus 60 is minus 36.01 plus 40j volts. Now we can convert that back to polar, because then that'll be in a form that we understand. Yeah. Because we got a negative real part, we know it must still be in that third quadrant. Yeah. And if you look at our diagram, start to throw together, we're looking at this being what was 104, so that's 104 long over that way. The real part, the other one is 60 that way, and if we resolve that parallelogram, we've still got a voltage over there in that quadrant. Yeah. Okay. So that's the voltage of the supply. 53.8 volts, angle 132 degrees. All right. I know it looks strange because you got 60 volts there, right? But that can happen because of the angle difference. Do you see what I mean? Yeah. Yes. Yeah. Yeah. All right. Remember, they're not all peaking at the same time. This is the issue with anything that becomes complex. Okay. So total impedance. How can we get that? Yep. We've got to have them in polar form. So E12 was I've got to divide that by 4.14. Angle of what? Okay, so I'm just going to sum that up, but we're using the fact that we can work on these power triangles and things and use the different values. As long as we get the complex arithmetic right, we can solve this circuit when we're only being given this 1 voltage here and the value, the impedance values of each of the components. So first of all, we got IR from the E13 voltage divided by the resistance, 5 amps. Angle assumed there was nothing. IC, we got reactance angle of minus 90 degrees, so we end up with 12 amps at plus 90 degrees. What we've done there is created a triangle where we've got a horizontal component from IR, a vertical component from IC, and we can add those together like we've done there in rectangular form this time and converted them to polar to get 13 amps angle 67.4 degrees. Is there another way we could have done that? Yeah, Pythagoras should have given us the 13 amps and then we'd have to done a separate equation to get the angle. So complex numbers allow us to do that all in one go. Yeah? Angle's important here. Using that current, we've then found the current through the inductor by Kirchhoff's current law. So added the two currents together to get 13 amps. That's what we've done there. Found the volt drop across the inductor, 104 volts, big angle. Then used that voltage added to E313 to find the supply voltage, which comes out at 53.8 volts. Seems strange that that's less than 2 of the other voltages in the system, right? But remember, when we'd normally quote a supply voltage, we'd quote it at 0 degrees. We'd make that one the 0 degrees one and the other one's relative to it. You must remember that none of these voltages are peaking at the same time, and therefore you can't just add up their magnitudes and think that's all going to look right, because it won't. And we've done problems like that before, and we'll do more in weeks to come. Then once we know that supply voltage and a line current, we can use that to find the total impedance of that system at 4.14 ohms, angle 64.6 degrees. Okay, so a nice little question, that one. Alright, happy with that? And I've got one more up here to do together, and then us over to tutorial questions, of which there's 3, 4 there, including a couple like the ones we're just doing now. So, this one, we've got a supply voltage 159 volts at angle 65 degrees, current I flowing through a resistor and inductor in series. It says Find the magnitude and phase of the current I, the magnitude and phase of the voltage across the resistor and the reactance, the active and reactive power associated with the resistor, the reactance and the source. Okay, so where are we going to start with this one? Yep, well done. ZT is equal to R plus XLJ. Now I'm going to put the numbers in. 45 plus 28J ohms. Okay. Convert that to polar because we might want it in that form. More than likely will. Yep. Now what can we find? I is equal to yeah, well done. So we got this 159 angle 65 divided by 53 angle 31.9. Yeah, I got 33.1. 65 minus 31.9. It's got to be more than 30. Yeah, fine. Okay. First of all, I've got a question for you. Is that current leading or lagging the voltage? And this one's 65 degrees, that one's 33. We go round anti-clockwise, so the voltage is ahead. Is that right for an inductive circuit? Yes. Okay, but it's always worthwhile just thinking, does that make sense? And that's a bit more tricky when the voltage you're working with, when one of the angles isn't zero, you need to think about where it is. Yeah. Alright? Always worthwhile looking at that. So what can we find now that we know I? Voltage drops, yeah. So let's go for VR then, shall we? It's I times R. And R is 45 ohms. The angle associated with that is nothing, but we'll write it in for completeness. I'll make that 135 volts. Angle 33.1 degrees. And that's true too. Current through a resistor and the voltage across it are the same. because the resistor doesn't alter the angle. Yep. VL I times plus our 3 angle 33.1 times yep 84 volts angle yep so what we found so far from what was asked for in the first place. Let's go back to this. Magnitude and phase of the current I, got that. Magnitude of the phase across the resistor, voltage across the resistor, and the reactance. The active and reactive power associated with the resistor, the reactance, and the source. Yep. So where can we go now? How can we find power? Which component has drawn real power? Yeah. So how can we get that power? Yeah, it's got to be I and IR, which is the same current because they're in series, times VR. Yeah. So that is 3.33 angle 33.1 degrees times VR, which is 135 angle 33.1 degrees. Yeah. And because they're in phase, all we're interested in is the magnitudes. The angles actually cancel each other out. And we got a power of 405 watts. Yep. No. Alright. So, having found that power, what can we know? What else can we find? We could do. Is there an easier way than that? What other value could we find? Now we know what E is. We know what IT is. A line current. We can find S, can't we? Yep. And again, the angles aren't really that significant. We can say that's 3. They aren't significant. Times 159. 477 VA. Yep. Now we can find Q, can't we? Yep. Right. Problem solved. Okay. Any overriding questions about anything we've covered tonight? Any issues?